Evening. So this is an update on tailings liquefaction work that I've been doing at the University of Toronto with my team of great students. One of them is in the crowd, Emmanuel, and one of the earliest slides is from his work. So you guys know this, but tailings liquefaction is a big problem. I was actually surprised to find out that it's the leading cause of failure in tailings dams, and both cyclic and monotonic. And this is Emmanuel's work that I mentioned. We wanted to put a dollar amount to this, so we looked at how the assumed residual strength, if you assume liquefaction will happen in these tailings, what you can count on after liquefaction, how that assumption, which is a big question, affects the cost of remediation. And we looked at putting in a tow berm and stone columns, and for 100 meters of a dam, that's $1.5 to $2.5 million. And that's an actual project, 3 estimates for cost, and that's millions of dollars. So that, some adjustment in that one parameter can make a big difference to the bottom line of a company. This is kind of an old schematic of all the research I do. I got to update it at some point. 2 lines of work. Basically, we look at liquefaction response. We start from element testing, modeling, and then eventually we get to some sort of a liquefaction strength against the state parameter. And on the second line, which is the main focus of the talk tonight, we look at in-situ tests. And again, going from lab testing to modeling, all the way to connecting the measurements of CPT in this case to the state parameter. And once we have those two, we can eliminate the state parameter from the equation and connect the liquefaction response directly to the CPT measurements. And once you get there, you can also look at case histories and see if all this modeling and assumptions that you did amounts to predicting anything real. Would the past failures and not failures corroborate your findings? I'm sure you all know this. It's 2023 and we're in Vancouver. But just for a reminder, the state parameter is the difference in void ratio from the critical state line. If you shear soil, eventually you get to critical state where there's no more dilation or contraction happening. And if you look at your current void ratio minus the void ratio at the critical state at the same confining stress, that is the state parameter. If it's negative, if you're below the line, if you're denser than the critical state, your soil is going to dilate to failure. And that means that you're going to have some extra strength that you can count on. And if you're above the critical state line, positive state parameter, your soil is going to be contractive. You're more prone to liquefaction. That's a big concern. On the right, you have manifestation of the critical state on the stress space. You have shear stress essentially on the vertical axis versus confining stress. The slope of this line between Q and P is M, the critical state friction ratio, which is equivalent to a constant volume friction angle. And M of 1.2 is equivalent to a phi CV of 30 degrees. That's kind of the rule of thumb number that we go with. And the way we do liquefaction assessment is you go to the field, you push the CPT, you estimate the state parameter from mainly the tip resistance, and then you use some correlation between the state parameter and liquefaction resistance, whether triggering residual strength or something else, and use that to design or assess the conditions of your site. This is the outline of the talk. Basically 3 parts to it. I'm sure I'm not going to make it to the 3rd part. It's a bunch of cool research stuff I put at the end. If anyone was interested, they can look at it later. The first part is the main part of it. It's about CPT. I'm going to start with drained CPT when we do CPTs in sand. And then I'm going to give you a pretty good method ready to be used. And I'm hoping someone will pick it up and try it out and see if it's crazy or not. And then I'm going to pose some questions about partially drained penetration. That's where the big problems are. And I don't have the answers, just more questions and things to think about. And if we have time, I'll get to show some of the second part of the liquefaction assessment, how state parameter relates to some of the properties, some of the liquefaction resistance out of the work that we did. And we're gonna close it off with that. So the first part is, why would we need a material-specific CPT interpretation? What's wrong if we just have a general correlation and just use it? So this is a database of calibration chamber tests. So you have a big tank, 1.5 meters or so in diameter, fill it up with sand. Everyone can hear me, right? I'm a bit away from the microphone. And you have uniform clean sands, as easy as they come, and you do some CPTs in there, and you correlate the state parameter, which you know because you prepare the sample, you know its weight and volume. And you correlate that to the normalized tip resistance. You normalize for overburden stress. And that's the range you get. That's the faded regression lines. Doesn't even have the repeatability scatter of the test. And if you do that at about 100 for the normalized tip resistance, which is roughly the threshold between contractive and dilative behavior, you'll have a range of state parameter which is about 0.12. If you look at the entire range of state parameters that you may have, this is about a third of it. I use a Toronto weather analogy. Toronto can be minus 20 to 40 year round in 1 year. And this is like me saying, okay, it's going to be 10 degrees plus or minus another 10. So could be 20, could be 0. Really not enough for a lot of assessments. And I'll show you some examples at the end, which is pretty close to that. That's where we are still. To get better than that, then you need to know which one of those lines you're on, basically. Right? So that's a big chunk of that uncertainty that you can deal with. When we started, we looked at some of the existing methods. Those of you who do this every day will recognize some of these methods. And we wanted to see how they do on that very same calibration chamber database. This is as low a bar as you can have. Most of these methods were calibrated against the same database or a part of it. So we just looked at how they can recover the state parameters that we knew in the database if you feed them the database. And we plotted the results of the histogram. Basically, the error is on the horizontal axis. So you want everything to be right here at 0, no error. And statistically, you want that bell curve to be sharp and centered in the center. 3 of these methods work fine. They're basically the progressions of what the late Ken Bean started with Mike Jeffries, and then the Pluis-Attal method came along, and then the cavity expansion was an extension of that. The widget that some of you guys use is an extension of that. And they do fine. There is some, if you were looking for one standard deviation, it's plus or minus 0.06 or so. But it's centered around the middle, and there's no bias. 2 other methods that we looked at have big problems. And one of them is the equations that's in the Bean and Jeffries book. I don't know why, because they were trained on the widget, basically. They should recover the widget results. They don't. So that's the red line. It kind of goes, no, that's the brown line. It has nothing to do with the middle. It's kind of unconservative most of the time. The other one is Robertson's equation from 2010. That one didn't do very well either. It tends to be on the conservative side, and it doesn't really capture anything in the middle. So you're probably better off just assuming a state. And this is a very low bar. This is as easy a test as you can do on this. So if you wanted to get to a material-specific one, do a little better, then you have 2 ways. You can do calibration chamber tests, which are difficult and expensive and messy, or you can be happy, like Mohammed here, and do CPT modeling. Doing CPT modeling, creating a model is very difficult. A lot of people, including me, have been trying for decades. But once you have a model, it's easy to use. And you can go one step further, and you can do some parametric and come up with some simplified equations, which you can basically use in Excel. We do both in my group, and we use calibration chambers to validate the model, and we use the model to extend what the calibration chamber test can tell us. To model the CPT with Norsand, we needed to pick a good software that could do this. Norsand is implemented in some platforms. It's in FLAC and Plaxis and other things. None of those can do CPT modeling because they cannot deal with those distortions that you can see in the mesh. CPT is a very difficult problem to model. And we picked Norsand as the model to represent soil behavior because it can do a good job. It's relatively simple. It has good penetration, especially in the tailings industry. It's becoming kind of the go-to model. And I was trained on it, so it was kind of natural as well. So we did the other thing, which is implementing Norsand in Abacus. So that was a good chunk of Mohammed's work. We verified it, so you want to make sure your implementation was okay. This is comparing the results, loose and dense, drained and undrained, to the VBA that is in the Bean and Jeffrey's book. So the implementation was okay. Now that you have the model, you first want to calibrate it. So it's forward prediction. We're not trying to do any monkey business going back and forth and trying to adjust the model so we get what we're hoping for. So you get a handful of triaxial tests, 6, 7, 8, something like that. And you calibrate, you get the critical state line, you calibrate Norsand to it. There are 5 parameters that you're looking at calibrating. The critical state friction ratio, which is like a friction angle. The slope of the critical state line lambda, which represents compressibility of soil. Elastic stiffness, which you can get with Bender elements, or in the field you can get from a seismic cone. Chi, which is a dilatancy parameter, depends on gradation and fabric, and H, which is a hardening parameter and depends on fabric. And obviously all of these are material specific. Once you do that, you do your model, then you want to validate it. So I'm going to show you some validation. And then once you have a model that you know works, you can use it to create some equations, do some parametric study, and figure out how you can have an interpretation scheme based on these parameters that you can always calibrate. This is the model. We're modeling our own calibration chamber, essentially. This does go more. Somehow paused. Oh, everything's locked here. How old is this laptop? Sorry, guys. I'm going to wait. I'm going to give it the benefit of the doubt.
That's easy.
I'm holding the clock. Oh, there, you made it. No, just go back. It doesn't matter. Go to the next one. There.
Next one? All right.
Yeah, let's not risk it. Okay, so once that model runs, you basically get a CPT profile. These are drained penetration, so we're not really developing pore pressures. You have a tip resistance versus depth, and you have a sleeve friction versus depth. You see the response to the state parameter, basically loose, medium, dense, and dense. The tip resistance goes up and the sleeve friction goes up. On the right, you see the normalized tip resistance against the state parameter. So we normalize the tip resistance that you get out of the CPT by subtracting the total mean stress and dividing by the effective mean stress. That's QP, that's the way this is typically done. And then you plot it against state on a logarithmic scale. And what you see in that figure is one of the biggest databases of calibration chambers on Ticino sand. It's from Italy. There are a few people who worked on that over a decade or so. And they're also the models of those same tests. And you can see that's basically the same range with the same amount of scatter. Scatter comes from different reasons, but it's pretty much not distinguishable between the two of them. So you can basically, with this model, do the work that you would do with calibration chamber, mined with drain penetration on sand. So we repeated that for 9 sands, and we plotted just tip resistance against tip resistance to see how we're doing. It's on the 1-to-1 line. There is some scatter, and I'll talk about that. And this was a big improvement over what we were doing with cavity expansion. So that's down there, my own PhD thesis. That's what the widget does basically. And this is an order of magnitude improvement once you go to the real cone model. Some of that scatter come from the calibration chamber data themselves. You can see this is back to the Ticino database. Those 2 red ones are 2 identical tests. So same density, same stresses. And you can see that they're about half of that range of scatter just by repeating that test. So a good chunk of that scatter just comes from the actual calibration chamber data. It's a very difficult test to run, very difficult to get good results. And that's how that model fares out against the rest of them. It's pretty comparable to the good ones. It's kind of centered around the middle, not better, not worse, and you can't really get better than the database. The point of something like this is being able to extrapolate beyond the empirical database, because now you have parameters that you can measure and you can account for differences. So you're no longer limited to the database that you train things on. We also looked at the sleeve friction. This is a chart that we use to estimate compressibility of the material from CPT data. You basically have the friction ratio from the CPT, kind of like the sleeve friction divided by its tip resistance. And that people have found out, starting with Ken Bean et al., that that's correlated to the slope of the critical state line. They had some data, David Reed added some data, which kind of made that figure. And our data are the blue ones on there with the range of parameters. So very similar to field measurements is what we're getting from our model, which gave us a little more confidence about how this model is working out. And then I can now do some parametric work and come up with some simple equations. The first thing we did is checking if QP is a good normalization of stress. Does it account for overburden pressure? Does it account for K0 differences? So we tried vertical stresses of 50, 100, and 400 kPa, and K0s of 0.4 to 1. And all of those collapse on that one line. So QP, according to the model, is a good way to normalize tip resistance. And if you fit a line to this, that line is exponential. And basically, you get two parameters, M and K. And these are the two parameters that we're going to try to get every time we're trying to get a correlation between Q and the state parameter. Now, I can go to Norsand parameters, and I can investigate how each of them would change that interpretation correlation. This is an example of the critical state friction ratio, M. So 1.2, 30 degrees is kind of the common assumption. What if it's lower? 1. What if it's higher? 1.5, which is common in tailings kind of on that end. And that can change that correlation. You can already see, if you start from 100, how much that can affect the interpreted state parameter. Now I can fit some lines to that, M's and K's, and in this case M didn't change, so the slope is the same, it just shifts up and down, and that's what K does. And then I can plot that against M, and I can get two equations there, and now I can use those equations to recover how the correlation is affected by the change in each of the 5 Norsand parameters that I'm looking at. Norsand has a couple other parameters, the Poisson's ratio, and there's a plastic unloading N parameter. Those we found out do not affect anything. So we don't need to worry about those last ones. The 5 that we do need to look at, this is the same structure of equations that Shuttle and Jeffries used. It's just this is an update that seems like working. And then once you get all of those parameters, you can multiply those, divide it by the base values, and that will give you M and K. Now you have a correlation. Now it's a big table, but this is something you can put in Excel. 10 columns of stuff, and you can get your correlation. You will end up with some iteration because a couple of these Norsand parameters are functions of the state parameter again. H tends to be a function of the state parameter, so you get a simple iteration in Excel, and that will solve it for you, no problem. I did put in an empirical fix. It's always needed to get good results. So we divided K by half, and this is when you go to the field and you use seismic cone to use your cone. This is when we were doing the calibration chamber database, most of them didn't have good elastic parameters. We used one that was kind of on the low side. If you want to go straight with a shear wave velocity measurement in the field, then you need this empirical correlation. And this makes everything clean, no assumption, no funny business. You can just go with your measurements. And that's how this recovers the calibration chamber database. There's still that scatter, plus or minus 1 sigma roughly, 0.06, 0.07 around it. And that's how you can do this. The thing that this method does, which I really like, is very easily you can also assess the error that not knowing these parameters can cause. Okay? So whether you didn't do the triaxial test that you should do to get Norsand's parameters, or if you didn't, but you know there's some variation in the field because of gradation changes, because of deposition changes, all sorts of reasons, you can very easily change some of these parameters and basically see how that can affect your interpreted state parameters. So you can do a very quick sensitivity analysis and get a sense for the risk you're taking but not knowing a certain parameter very well. And what I did, I kind of went for the whole span of parameters that you could have. So m goes from 1 to 1.5, lambda goes for 1 to 0.01 to 0.2, big range, and I ranked these parameters. And you can see lambda is the big one. It has the biggest effect, and that's what Ken Bean picked on empirically back in the 80s. Plouz et al. Came along and they picked on m. They realized m has a big effect. So their equation has m, the critical state friction ratio, as something that needs to go in. And then in 1997, Shuttle and Jeffries, in their cavity expansion model, picked on IR, the elasticity. And you can see these are the three that do have the biggest effect on the interpretation. And that's what comes out. Chi and H have a lower effect, and that's a good thing, because chi is influenced by the gradation, and it's also influenced by fabric. If you're going from lab to the field, there's an effect there, and so is H. And that tells me that if I do stuff in the lab, whether in my triax test or if I'm doing calibration chamber or anything, the effect I'm going to get on transitioning to the field because of all the fabric differences, whatever those mean, are not that big. And even if they are, I can turn the H knob a little and assess how big those may be. Just to get a sense, this is the same calibration chamber database in the background. And I then went with a very stiff material and a very soft material by turning all these Norsand parameter knobs. And basically, if you do that, even within drain penetration, for the state parameter of negative 0.05, which is the threshold between dilative and contractive behavior, you can cover the entire range of tip resistance. So this material-specific interpretation can really control a lot of things. So validation, close to home. Fraser River Sand, Canalex project. This is the Massey site. And we have frozen samples there. And I'm showing you, there's 6 CPTs here, so you have a range of tip resistance, a range of normalized tip resistance, and a range of state parameters interpreted. Those are the Norsand parameters that we plugged in. Those are tests I did at Golder way back. And the method that's proposed, which is the one in red, is very consistent with the widget, and it's very consistent with Plouz et al. This is expected. This is a clean sand, really not that different from what was done in the calibration chamber. And the methods are doing the same. The frozen samples are looser. I don't know what's going on there. That's something we could discuss later. But it's at least this is doing the same thing other methods are doing. But we were doing this for tailings. And we're getting tailings calibration chamber data now, which is great. And David Reed's group out of Western Australia, Ayala et al., 2022, they published 2 sets of tailings data on gold tailings. These are miniature cones, small chamber, and drain penetration. And that's the data they got. This is how Plouz works against that. So it's quite unconservative. You're off by about 0.1. So you're going to think that the material is much denser. And this is with the right parameters. I'm not going with an assumed M of 1.2. I'm putting in the correct M that we measured. That's what the widget does. And this is what the equations do. I think that's a bit lucky. I didn't expect them to do so well. But they do fine. They're doing at least as well as the widget does, and they're easier than it. This is the platinum tailings, same story. And then that's the widget, and this is how these equations are doing. So they do really well in drained, and they're doing fine in tailings. So Plouz et al. Is a good method. you got to put in the right numbers. If you don't, you're adding to your error. It's good for screening level quick. You get some estimate. The widget is good. I'll come back to the widget shortly. But you do need to calibrate to Norsand for the widget. And these equations are at least as good. They're easier than the widget. There's no, you don't need to run anything. And the good thing about them, even if you didn't calibrate to Norsand, you can estimate how much error you may have by looking at the range of probable parameters that you're looking at. The other methods that we looked at, I wouldn't use them on tailings. Now, the big one, partially drained CPT. So these are all great. There's a great method, some answers there, there's some improvement, making life a little easier. Now I'm going to make life difficult again. This is stuff where it's a discussion. I don't have any good answers here, just more questions and stuff to look at. So one case study. This is something in a gold mine somewhere in Canada. Some of you may recognize it or not. Contact did some really good work. They did different rate CPTs. They did some very good sampling. This is piston sample with air injection at the bottom to cut off the sample and fight suction. So we got some really good samples out of the ground. They're vein, variable vein as well. I'm not showing any of those here. The site is relatively uniform as far as tailings go. The upper part is thickened tailings, so they changed the process. You get thickened tailings on top, very uniform and nice. Below about 9 meters or so, this is traditional slurry deposited tailings, so more variability there. Based on where we had those samples on the right, we picked 2 layers to focus on. There was a bit of a transition there, we kind of skipped that. So the upper layer, which is in the thickened tailings, pretty uniform. Developed excess pore pressure, so that VQ is normalized pore pressure. So you get some excess pore pressure. There is something undrained or partially drained going on there. And that's Plu's method, state parameter. It's saying it's on the contractive side. So this is trouble, according to Plu's. That line at negative 0.5 is the threshold. If you're to the right of it, you're in trouble. If to the left, you're okay. The lower layer, no excess pore pressure. So pretty much drained penetration as far as we could tell. And the CPT is saying you're on the dilative side. The big thing here is how far those samples were from the CPT. The samples are saying your material is very dense. These are pretty good samples. My first reaction would be, yeah, but how good are they? And that's something I'm going to explore a little more. Bottom seems fine. There's some spatial variability, I'm sure, everywhere, and probably some at the bottom, but there's no big question there, at least as far as the Plu's method go. I'll get back to that as well. So why are those so off? Why are the samples saying this is a very dense material and the CPTs are saying it's contractive? So that's the gradations. This upper layer was a little finer. As you saw, it developed pore pressure. It is that orange line is the kind of representative thickened tailings line, so very nicely around that. The lower layer, it's a wider range gradations as you expect, and it's a little coarser, and only that much difference. This is, if you're looking at a tailings site, these are really the same stuff. It's really hard to tell, but that was enough to make that difference in pore pressure response, which is the first thing that really scares me. And then we did dissipation tests. If you look at T50s here, it's kind of consistent. The upper layer has a higher T50 than the lower one, and they're both in the drained to partially drained range. You're less than 30 or 50 seconds T50, which is kind of where you transition to undrained. The critical state lines are fortunately pretty close. This is testing that we did and WSP did. They're turning out to be pretty close. And where those samples are and where we did our work, they're kind of where they're on meet. So there's not a big question around where the critical state lines may be. We're still going to investigate this some more, but they seem to be pretty close. That's at least not one of the variables. So what do we do when you have that big problem with the samples not matching the CPT interpretation? You do some calibration chamber testing. So you collect a lot of tailings in those big blue drums from the site, and you bring it to U of T, and that's our chamber. And you get some great students to work on it, and then you push a cone in it. That's the guy who's leading that work. He's graduating soon. Our chamber is 1.4 meter in diameter. This is Golder's old chamber from Calgary. We shipped it there and built a lab around it. 1 meter high, and you can apply triaxial boundary conditions, basically a membrane around it, and vertical loading, and then push a cone. What we're using for it as is using rigid walls. We just didn't want to deal with that horizontal vertical membrane, less leaks and stuff. It's hard as it is. So we're doing like an odometer, vertical load and having a rigid wall. We're measuring horizontal stresses, so we know K0. Do not worry, Adrian. That's the gradation of the calibration chamber samples that we got. So it's finer than both of these materials. It's kind of on the upper range of the thickened tailings. So it's a little finer. We push the cone. This is the results. It's not this is our very first tailings test. These are, by the way, very fresh results. I'm sharing with you because it's very exciting. So we pushed it. It seems a little denser on top. In the middle, we stopped and did a dissipation test. That's why you see that spike there. And pretty typical results. You have tip, sleeve, and pore pressure. There was 100 kPa back pressure in there, so that's kind of your zero. On the right is the void ratio. And this is important because we want to be able to trust those void ratios. The circles are samples that we took after testing. The black dashed line in the middle is the average of those samples. The blue and the red are what our bulk void ratio, which we knew from the weight of the material we put in, its water content, its volume, and all those things. And they agree very well. And that makes me trust the sampling void ratios because their average is also agreeing with the bulk. So that means that the void ratios that we got from the chamber aren't too bad. And this is just the chamber data in black thrown on top of the field data, just for comparison. You know, it's just hanging in space. The ranges are very similar. So tip resistance, the low range is very similar to what we saw in the field. The high range is very similar to some of the tailings that we saw in the field. Same goes for sleeve friction, same goes for pore pressure. So really, if you move this up and down, the maximum and the minima are pretty close and comparable to the field. And interestingly, so are the state parameters that we got from the sample. So we have some states that are very dense, and we have some states that are on the loose side. So again, if you stretch that and kind of took liberty with where those are, very comparable. So very consistent results between the chamber. That makes me, not quite throw out the sampling that was done in the field. And I don't have an answer for that difference, but I do have some interesting stuff to look at. That's a question to be answered. Why is that happening? Now, if I come back to the CPTs, we looked at some different rate CPTs. And their CPTs at 0.2 centimeters per second. That's 1/10 of the standard rate. Their CPTs at the standard rate, 2 centimeters per second, at 10 and at 15. And what was very interesting is if you look at the fast test, let's look at the upper layer. This is the one that developed pore pressures in the standard CPT. When we did the fast test, the tip resistance went up. There's a question with the pore pressure there. But if I interpret that, this is now this is the slow test I'm looking at. That's the orange one. Tip resistance went up when we slowed down. So this is now pushing this CPT towards drained. We're killing the pore pressures. So pore pressures are low. We're removing that partially drained question. And what happened is, if I interpret that, and this is back to clues, I'm going to come back to looking at my method, but you go across the line. This is no longer considered to be liquefiable. And if you look at all the other ones, which are the standard rate and all the faster ones, they're still considered to be liquefiable. And this is basically because our normalization is not working. We're not doing this partial drainage right. Depending on the rate, we're getting a different state, and this is driving the project basically. Now, if you look at the bottom layer, it's the opposite of that. So look how the standard one just crosses here and comes to the side of the slow one. So the slow test here is still drained, and so is the standard one. And all the fast ones are now undrained. And interestingly, they're pretty much where the other one is. So if you look at the undrained line, and you look at the drained line, you're basically going to the two sides of our criteria threshold. And the difference is about 0.1 in the state. So you're either on that side or this side. And this is all driven by partial drainage and how we're not correctly accounting for it. So 0.1 for missing partial drainage. And now another 0.1 for missing material-specific behavior. This is now the slow test. So I'm looking at drain penetration again. And if you use my method, which I just explained to you, instead of Plu's, which is on the left, you're back to both of these now being pretty much liquefiable. So we went a long way, and luckily we had picked on at least half of this to be liquefiable. So basically what my method is telling you is that, yeah, this is probably all liquefiable on that side if you get rid of the partial drainage problem and then do a material-specific one. And this is consistent with what we saw in the chamber tests from that gold and the platinum data from Ayala et al. Again, the Plu's was kind of on the unconservative side by about exactly that same amount. This is another gold tailings, and this is exactly how much difference we're seeing on that side of it. Now, why are we so far from those samples? I have no idea. We're going to do more calibration chamber tests. I'm going to take the calibration chamber material and try to determine its critical state. Maybe that's somewhere else. That's an open question, at least as far as I know. One last summary slide on that, then I'm going to skip through a bunch of things, and so we can finish on time. This is a summary of all the data that I showed you from the site. So you're looking at the upper layer here on the left, the lower layers on that side. This is based on the measured void ratios, the measured states. And when you go up, this is kind of the drained test. Tip resistance goes up when you go to the drain side, which kind of confirms that you're in a contractive material probably. Remember, pore pressures were also positive. And then when you go towards the undrained side, you're lower. These black ones are the chamber data. Very low compared to what we're getting. Those are what the widget would give you, drained and undrained. So the widget's doing a decent job capturing that distance. The difference between drained and undrained, I think it's doing a pretty good job, but it's off like everything else. It's way to the right. If you go on this tip resistances into either of these lines, you're going to get a positive state. So whether it's a problem with our samples and not knowing the critical state, or the CPTs, I don't know. I tend to always end up trusting the CPT and then be biased. But now I have chamber data, which is kind of also very reliable. I don't know, to be discovered. There is a problem. The points there were that by missing partial drainage, at least in this one site, we can be off by 0.1 in the state, which is enough to put us across the threshold. So we'll change our decision. By missing the material-specific nature of interpretation, again, you'll also miss the state parameter by about the same amount. So both of these are important. Each of them is big enough that it can completely change the outcome of your analysis. What really worries me is how easy it was to go from drained to undrained or partially drained penetration in a tailings with the standard rate. And that's why I always like to see different rates of CPTs tried. Contact can do this fairly easily. I would at least do 3 rates, find a test site and try them out. And some sampling gives you a lot of perspective. Now, I have this thought thing here. It's more of a discussion point. I'm going to skip it. This is on partial drainage and where troubles may be coming from. I have some thoughts on normalization and whatnot. I'm not going to bother you with those things, but I'm going to emphasize doing more than one CPT rate, There's no way we can figure out where we are on the partially drained range with one number. No matter how hard we try, there's so much stuff going on. At least get 3. That will give you a sense of how much your tip resistance can change because of that. Seismic CPT, we need elasticity. Obviously, always do that for good interpretation of the state. Then dissipation tests, because you need C sub H to figure out where you are on the partially drained range. And on the step sampling, even if the samples aren't great, it will still tell you so much. It's an anchor that you can tie things to. So this is the second part of the research. This is quick, don't worry, we're almost done. This is now, I have state parameter. So if I go back to my initial plan, I figured out how the CPT tip resistance is connected to the state parameter. Now I'm going to figure out how some of these liquefaction responses are connected to the state parameter. So we can kind of compare to what happened out in the real world. So we looked at a few things. I'm basically going to show you 1 or 2 slides out of each journal paper. And these are coming out or are out already, so you can see more of those. Just again, seeding some thoughts without giving you a whole lot of detail on stuff. We looked at 2 sets of materials. On the left, you see a natural soil. This is from a quarry in Huntsville. It's 3 hours north of Toronto to kind of get to where you can get materials. We got fine gravel all the way to fine sand. And then we mixed them and we created mixtures. I didn't want to mix kaolin and sand. I wanted to source them from one place so it's naturally reasonable. On the right, we have tailings. So this is the base metal tailings from somewhere in Ontario. And again, we have the sand side, which is a fine sand, and we have the silt side, and we have 3 mixtures in between. And we ran a whole lot of tests on these. E-min, E-max, as a function of fines content or gravel content, and D50, you can see the mixtures always have the most compact gradation. And then the silt and the sand on the 2 ends, or the gravel and the sand on the 2 ends, are kind of higher. Those uniform ones end up having a looser compaction. So those mixtures are always the stiffest materials, the most compact ones. We looked at particle properties, particle shape, mineralogy, because we wanted to make sure that there's no big bias as you go from gravel to fine sand or as you go from silt to sand. And we didn't pick up on the silts being much more angular than the sand. We wanted the particle size to be pretty much the only variable here when we're looking at things. And that was pretty much confirmed. On the left, you see how critical state lines changed. In the natural material, going from fine sand to gravel, these are all the uniform stuff. These are parallel gradation curves. So the only difference is really particle size. They're scaled versions of each other. And as you expect, the critical state lines are pretty much the same. There's no big difference among them. This is within the range of error, basically. But the mixtures were quite lower. And at least one of them, which was the most well-graded mixture we could get, with a bit of a humped gradation, was very flat. So if you're trying to do state parameter interpretation or something, that's the gradation that gives you the limit on stiffness. No, it's not the coarsest one and the finest one. It's not the top and bottom of the envelope. It's the one in the middle with the best kind of fractal gradation. On the tailings, again, the 2 dashed ones are the silt and the sand. Now, the silt was higher. It was steeper. We know this. When you go to fines, they tend to become more compressible. But then again, the mixtures of them were lower. They were stiffer. So this is a problem if you're trying to figure things out in the field and kind of envelope your properties. The other thing we looked at was cyclic liquefaction resistance. This is Methan. He's with WSP now. And these are his data. What happened to that? This is the laptop's fault. So that 20% was up here somewhere. I don't know how it shifted there when we transitioned laptops. That's how we got our residual strengths for later. But basically, cyclic simple shear testing to liquefaction, 3.75% strain for liquefaction triggering. And after that, we did a post-cyclic monotonic test. The numbers I'm going to report in the residual strength are all of these at 20% strain from the end of liquefaction. So it's not a real residual number. It's just kind of some consistent number that we picked. Oh, this one's right now. Great. I don't know what happened there. So that's how we picked it, just to be consistent. You see this material is dilating. There's no real residual value there we could pick. Now, that's a long paper. It's coming out soon. But we were trying to pick on gradation effect on liquefaction triggering, cyclic resistance ratio. And we wanted to look at other effects. And all we found is that if you zoom out and go to the standard scale of cyclic resistance ratio, which is usually 0 to 0.6, simple shear is very flat compared to triaxial, compared to some field data. And everyone knows that simple shear is lower than critical state than triax, and their corrections factor, but the difference is density dependent, and the difference is in a way that really, when you're doing simple shear, you're liquefying everything anyways. There's really little strength gain as you make this material denser in the simple shear. This is not just our data, there's a lot of data up here. All the kind of mixtures and stuff that we could find where we could have all the parameters and we trusted the source. So this was an interesting thing. So I do a lot of simple shear. I haven't given up on it, but it made me think about, it's the reference test we go to when it comes to things like cyclic loading and liquefaction. It's quite challenging. Last of them is the residual strength. Again, without going into a lot of details, we're looking at those same materials. This is the Edgerton-Boulanger database of residual strength with their curves on it. So a lot of you are familiar with this. And all I did is I took that 20%, which is it's just a reference number. It's not the real residual strength or anything. And we looked at all those different gradations on what they produced, and we threw it on top of this. We converted our densities to CPT tip resistances based on equations that are in the monograph. And this was interesting. So the shape of those curves coming out of the lab tests are very consistent with the shape of the curves that these guys drew and everyone uses. So that's one. The other one is that the lab data do not really disagree with the field data. You can see some of them follow a lot of this. These ones are kind of aligned with it. There's no real disagreement among them. And the way I see this, and you can see here in the tailings, for example, the sand is on the strong side. The pure silt is on the weak side. If you look at this, the gravels are kind of on the strong side, and the sand, the fine sand, are kind of on the weak side of this. And I don't think this is something you want to just pick and use right now. But I do think that running those tests and then kind of putting it on the background of the case histories will at least give you a sense of whether the material you're dealing with may be on the better side of things or maybe on the worse side of things. You can kind of gauge your conservatism maybe. If you understand how your material may be different from other materials, I think that's kind of interesting. So to wrap it up, most of these parameters, they're material specific. These materials are different. They're not all the same thing. That's driven by particle mineralogy, particle size, particle shape, all those things. High quality sampling lab testing, even if we don't end up using it directly, I think it can be very useful. Calibrating to things like Norsand, just getting a pail of material from the site, reconstituting some samples. That's, I don't know, $10,000, $15,000. A lot of companies have their own lab. I think it's worth doing on a lot of projects. I don't see why we wouldn't do it. If you want to have if you have a range of gradation curves and you're trying to pick two to test, the top and bottom envelopes are not necessarily the best ones. You may want to pick one of the mixtures. They tend to be the, most, the stiffest ones. And then one of the more uniform gradations is probably the weakest one. If you want to kind of envelope your properties, it's not just with fine end and coarse end. Constant volume cyclic simple shearing and monotonic simple shearing, they're quite challenging. I have a ton of slides that I could share with you and look at and spend hours on simple shear. We're spending a lot of time on it. But it's a challenging test. It's not a trivial test. Doing a good one is hard, and even when you do one, understanding what happened is not trivial. It's not necessarily, the constant volume simple shear test is not necessarily what we think it is. And then residual strengths, again, if you put them on the background of case histories, I think it can be quite informative. I'm going to skip over all of these fun researchy stuff. These are the references. About half of these are out. Half are in publication or so at different stages. I'm a lazy writer, and journals are horrible at getting stuff out. You can always email me, Q of T, and I'll send you stuff if you wanted to look at them. The stuff I showed you, I've been collaborating with Professor Mark Talasnik out of Technion, and he has these sensors that are super cool, and we're doing a lot of cool stuff with them. Measuring horizontal stresses is one of them. Alex C has been great in helping me. He trusted me early when I started at U of T, and that mattered a lot. And Contech has been a huge support, both funding and equipment and thought and everything. And all those companies that have sponsored my research and are still doing it. And of course, all these graduate students, they're the ones in the chamber. This is the second generation. I was looking at this picture, and most of them are now somewhere not quite graduated, but kind of, progressed. There's quite a few new faces now. Anyhow, if you're in Toronto, stop by the lab. I would love to chat and see what you're up to, and get you guys to give a talk to our group. And that's about it. Thank you.